Hello, so this is 2.25b, where we're going to be finding the potential at a distance z above the center of this charge distribution seen right here, that's uniform line charge. So we're going to start this by using the equation v is equal to 1 over 4 pi epsilon naught times the integral of lambda r prime over script r times dl prime. So we know our script r here, the magnitude of it as z squared plus x squared. And since we know that it's a uniform charge distribution, this lambda can come out, and we know that this dl is only in the x direction, so it would be equal to dx. So we could put everything in. Okay, and this integral is going from negative L to L. So this is basically an integration problem at this point. We can start by drawing a triangle where theta is going to be up here, and x prime and z prime on these two sides. And we're going to have the magnitude of your script r on this side. And this gives us tan theta is equal to x prime over z, which we know is x prime is equal to z times tangent of theta. And we can find this differential element is equal to z dx prime is equal to z secant squared theta d theta. And just for reference, later on we're going to be using secant theta is equal to z squared plus x prime squared over z. So we can do this trig substitution for this integral. Z secant squared theta d theta, substituting in for dx prime, over the square root of z squared plus z squared tan squared theta, substituting in for x prime. And we can make some cancellations here with just by writing everything out first. Just by taking this z squared and factoring it out of this term, and coming out of this square root. So we're going to just have 1 plus tan squared theta here, all with this differential element of d theta. And these are going to cancel. And we can also make a substitution here for secant squared on the bottom. D theta And this gives us, these two are going to cancel out, and this is secant squared is also going to cancel out with the secant theta on the bottom in the denominator, and we're just going to be left with a secant theta d theta. Now from here, we can multiply the denominator and the numerator by tan theta plus secant theta for a substitution in just a second. If we take everything out of this parentheses, it will be secant theta tan theta plus secant squared theta over tan theta plus secant theta d theta. Making another substitution here. Tan theta plus secant theta would be equal to secant squared theta plus secant theta tan theta times d theta. Make another substitution here, and this is just going to give us 1 over v dv. Now this is a pretty simple integral, natural log of v from negative L to L, but we have to put all of our substitutions back. Natural log of tan theta plus secant theta from negative L to L. And we can make use of our trig subs at the beginning with a natural log of x prime over z plus z squared plus x prime squared over z. Oh, sorry, you can't see that. From negative L to L for this x prime. So we can plug everything in now with a natural log of L over z plus z squared plus L squared over z minus natural log of negative L over z plus z squared plus L squared over z. We can combine these natural logs to be L over z plus z squared plus L squared all over negative L over z plus z squared plus L squared over z. And finally, we can make this natural log. We can take a 1 over z out of both of these terms in the numerator and the denominator, canceling them out, giving us L plus the square root of z squared plus L squared in the numerator, and in the denominator, negative L plus the square root of z squared plus L squared. And now we can plug that back into our original potential, giving us lambda over 4 pi epsilon naught times the natural log of L plus the square root of Z squared plus L squared over negative L plus the square root of Z squared plus L squared. So that's the first part of the problem. The next part of the problem is to take the gradient to find the electric field at this point P. The negative gradient. So we know that our potential here is 1 over 4 pi epsilon naught times lambda times this natural log of L plus Z squared plus L squared minus L plus the square root of Z squared plus L squared. So when we take this gradient, we're only doing it with respect to Z in the Z hat direction. Just putting this potential in, Z squared plus L squared all over negative L plus the square root of Z squared plus L squared. So this constant term can come out, giving us negative lambda 4 pi epsilon naught Z hat times this derivative of the inside, which would be well, actually, it would be a little bit easier if we fully wrote out this natural log. So if we did natural log of, that's supposed to be here, Z squared plus L squared minus natural log of minus L plus Z squared plus L squared. And we could do this derivative first, and that's going to give us 1 over L plus the square root. I'm going to write it with a 1/2 this time. Z squared plus L squared, the 1/2 times Z squared plus L squared to the negative 1/2 times 2Z by applying this chain rule. And similarly, we will be getting minus 1 over L plus Z squared plus L squared to 1/2 times 1/2 Z squared plus L squared negative 1/2 times 2Z. And now we're just going to take this constant down again. And we can actually factor out Z over the square root of Z squared plus L squared in the denominator times this value, negative L plus Z squared plus L squared minus L minus the square root of z squared plus L squared. Just doing a bit of simplification. All over z squared plus L squared minus L squared. And some things are going to cancel. These will cancel. These will add together, and these are going to cancel too. And we're going to be left with L. These negatives are going to cancel out with these L's. Lambda over 4 pi epsilon naught over, there's a z here, z over z squared times the square root of z squared plus L squared in the z hat direction. And these two z's are going to cancel. And we're going to be left with 2 pi L lambda over 4 pi epsilon naught times 1 over z to the square root of z squared plus L squared, all in the z hat direction. And that's your answer. Thank you. Oh, actually, before I make this mistake, there was a negative L here. And that is our answer. Thank you.